Hi, welcome everybody. My name is Marta Suarez. I am the president of the Dynamic Spectrum Alliance, and I would like to thank you for attending this webinar today, titled Dynamic Spectrum in Aerospace Networks. So a few words about DSA. The Dynamic Spectrum Alliance, DSA, is a global, cross-industry, non-for-profit organization advocating for laws, regulations, and best practices that will lead to more efficient utilization of a spectrum, fostering innovation and affordable connectivity for all. Our mission basically is to make spectrum abundant for broadband, and we have 3 specific goals. So one is to connect the next 4 billion people, and we are convinced that spectrum sharing is a key enabler for that goal. We also would like to stimulate wireless innovation for next generation broadband and accelerate an inclusive digital economy. This webinar session will evaluate the use of dynamic spectrum sharing using aerospace solutions to promote innovation, competition, and rural connectivity. In this session, we will learn about temporospatial software-defined networking for the management of aerospace networks, such as HAPS and non-geostationary satellites. We will discuss about how dynamic spectrum sharing in millimeter wave bands can promote rural connectivity while ensuring coexistence between this and future users of the band. Finally, we will consider some steps that regulators and spectrum authorities can take today to enable this very, very exciting future. I would like to thank the speakers that have kindly accepted to join this workshop, and also Loon for making this possible and sponsoring the session. Thank you, Loon. The DSA webinar, this webinar is brought to you as part of our 2020 Global Summit campaign. The DSA Global Summit will be a virtual event. It was planned to be in Paris, but due to the situation, we had to switch to a virtual event. It will be during the first week of November. The agenda is published in our website and registrations are open now, so join us. Let me clarify also some logistic details for this session. Speakers and the attendees are in different virtual rooms, so please write all your questions in the chat and a moderator will transmit them to the speakers. We will use the social media hashtags DSA Global Summit and Dynamic Spectrum during this webinar, and it will be recorded and available soon in the DSA website. Well, after these remarks, let me introduce our first speaker, Jameson Dempsey, Government Affairs Counsel at Loon. So welcome, James, the floor is yours.
Thank you very much, Martha, and thank you to the DSA for having us. Wes and I are privileged to be a part of this conversation. Let me very quickly show my screen, and then I think it's screen 2 here. Can everyone see the presentation? I don't know if I can get a thumbs up, but maybe Martha can say. Great, okay, perfect. Excellent. Well, thanks again for having us. We really appreciate it. And today we're going to be talking about a few issues related to temporospatial software-defined networking and dynamic spectrum for aerospace networks. As Martha mentioned, I'm Jameson Dempsey. I'm a Government Affairs Counsel here at Loon. And what we're going to do today is cover a few issues, as you can see in the agenda. First, we'll talk a little bit about Loon, who we are and what we do. Then we'll talk about aerospace networking for HAPS and NGSOs. Next, we'll talk about the suitability of millimeter wave bands, particularly E-band, for dynamic spectrum management. After that, we'll talk about how regulators can create an enabling regulatory environment for aerospace dynamic spectrum access. And then finally, we'll close with a Q&A. My understanding is we'll take a break in the middle of the presentation for Q&A as well, to talk about some of the technical issues that you'll hear from my colleague, Wesley Eddy. Okay, so let's jump into it with an overview of Loon. Loon is an independent subsidiary of Alphabet and a sister company of Google. It began as a project within X, Google's moonshot factory, but spun out in 2018 as a separate bet, alongside other bets such as Waymo for self-driving cars, Wing for drone delivery, and others that you can see on the chart here. Loon's mission is to connect people everywhere by inventing and integrating audacious technologies. But what is Loon? Loon is a network of stratospheric balloons that delivers internet access to unserved and underserved areas and in response to disasters all around the world. We're building a new layer of connectivity in the connectivity ecosystem between terrestrial infrastructure and satellites, and we serve as a complement to both. In fact, we're not an operator. Instead, we partner with operators to help them extend their networks to new customers and new places. But how does Loon work? I'm sure you're asking. This diagram helps to explain. Loon takes the fundamental features of a cell tower and places them on a balloon flying at approximately 20 kilometers in the air. Our payload includes both access and backhaul antennas. On the access side, each one of our balloons includes an LTE payload that can cover an area of 13,000 square kilometers on the ground, extending the networks of our partner operators into unserved and underserved areas. For backhaul, the balloon forms a mesh of E-band links, which connects to a ground station integrated with our partners' networks, as you can see here on the chart. You could think of Loon as a cell tower floating in the sky. I'm sure you're also wondering how our balloons get to the areas that they serve and how they stay there. Well, our balloons navigate by leveraging powerful machine learning technology to ride wind currents at different layers of the stratosphere. This technology allows Loon to launch its balloons from its launch sites in the United States to our service areas in places like Kenya. The balloons remain in service for an average of about 150 days and can station seek in the area that we serve by going up and down in the stratosphere and staying in just around the same area. When it's time for the balloons to come down, we coordinate with local civil aviation authorities and teams on the ground to safely land and recover our equipment. Loon is not a science project. It's not an experiment at this stage. It's now a robust system that's been tested and improved over years of experience with active deployments. As you can see here, since 2013, we've flown over 1 million hours in the stratosphere and over 40 million kilometers of distance. This diagram here, which looks like a bunch of spaghetti on the world, shows our flight paths between just 2018 and 2019. Working together with our M&O partners and subject to duly issued licenses from national regulatory authorities, we've served over 300,000 users on multiple continents, as you've seen here. In Latin America, we've provided disaster recovery solutions. We've also done the same in Puerto Rico, and we've announced our first commercial launch in Kenya with Telkom Kenya, as you can see on the lower right. And here's an example of our mesh in action. You can see links spanning 4,000 kilometers and over 20 balloons in order to provide connectivity on the ground and reach hard to serve areas. And today we're here to talk about the software behind Loon's mesh network, the brain of our system, and the implications of that software for the future of aerospace networks and dynamic spectrum management. And with that, I'm going to turn it over to my colleague, Wes Eddy, who's going to describe a little bit more about the technology behind our mesh.
Jameson, we're not seeing the slides.
Oh,
there we go. Okay.
Perfect.
So, hi, I'm one of the engineers that's working on our software-defined networking solution. And I'm going to be explaining some of the problems that face air and space networks. I'm going to describe our unique approach that we've come up with to solve these kinds of problems for Loon's HAPS network, and that also works for other challenging systems. And a big part of this is how we enable dynamic spectrum access as integrated part of software-defined networking controller. So I would go to the next chart. So our work on these topics actually began in Alphabet 6 years or more ago. Loon has been specifically advancing HAPS, but more broadly, we've also done work on other types of aerial platforms, LEO satellite constellations, terrestrial mesh networks, and other types of challenging networks. All these new types of platforms are being deployed to extend the reach of traditional internet and telecommunications applications. They're supporting uses in cellular for 4G and 5G backhaul from remote locations, providing connectivity for private and enterprise networks, consumer internet, and also supporting aircraft, Internet of Things devices, and other kinds of uses distributed widely around the globe. At Loon and in Alphabet, we saw a number of similar problems across these networks, and we began designing common solutions that would work across the board. So these are some of the key problems facing aerospace networks. Number one, there are fundamental issues applying traditional network routing. What I mean by that is mainly from the internet world. There are a lot of routing and data transfer protocols that have been developed over the years. They mainly have some common properties and assumptions that break in aerospace networks. Distributed routing and decision-making at each node based on a local view are key design properties in traditional networking. For a large network where there are a lot of moving infrastructure nodes and links that are prone to failures or errors due to weather, obstructions, interference, or other physical issues, these kinds of distributed algorithms can make bad decisions or even fail to converge completely to usable solutions, since each node in the network only has a partial view of the information. They work fine when the core and distribution layers of the network are fairly static, but have trouble when there are high dynamics. Second, even if the routing system can be tuned well, there are inevitably at least brief disruptions due to the networking protocols having to do sensing, detection, and error recovery in reaction to changes in the physical links. To do this, the protocols use timers, back-off algorithms, and have other delays as parts of their designs for robustness. In a layered network, even small disruptions in the lower layers ripple upwards and can cause timeouts and other performance issues for the upper layers. So the result is users see poor performance even if the links are most of the time performing well. Third, internet routing protocols don't know anything about spectrum regulations and avoiding interference, so they need to work in conjunction or coordination with other methods to determine how to point antennas or antenna beams, and the layers making routing decisions have very idealized views of the links that don't take into account RF or physical properties at all. And finally, fourth, you can build a large system with a number of point solutions for individual aspects of this system, but it creates complexity, operational issues, and has high cost to maintain. So we have a different approach. Next chart. Okay, so in particular, some places where we see these types of problems are in mesh networks, where the infrastructure is in motion and the connectivity in the middle of the network is highly dynamic. So the routing over the mesh itself is also dynamic, and the users or other parts of the system might also be mobile and moving between beams. Some examples are HAPS, like the Loon network Jameson described, but also non-geostationary satellite networks, where the constellations have cross-links and inter-satellite links. There are parallels between these types of networks, both physically and in spectrum access and regulatory issues that face the networks. Next chart. Okay, so this is an example of an internet protocol stack. You have a mixture of protocols at different layers that work together but also encapsulate functionality, and that can end up hiding some information and events that the layers individually know about. So at the bottom is the physical layer with actual links and radio frequency devices, and the functionality is progressively built up until you reach the application layer at the top. This is where you have like a web browser that a human interacts with, and that's where you can experience a long stall doing something like simple, like resolving a domain name. Here, like it's a user trying to type www.google.com. That causes a lot of things to happen at the lower layers. Down below in the low layers, even if there's only a brief disruption, it can cause major problems due to timeouts and issues that ripple upwards. So if you advance to the next. Okay, so here we go. This is a plot of a TCP connection progressing over time. Basically, data transfer should be going upwards as you move to the right if the transfer is working properly. Well, what happens here with the little letter R's are retransmissions, and those can start to be triggered if there's a brief loss event. And the problem is that the retransmissions wind up being spaced further and further in time due to a backoff period. So if the timing loops in the protocol retransmit very quickly, but it's too quickly for link conditions to be repaired, and they start to back off, then the ability to use a link when it is finally repaired is greatly impeded because it takes longer to retry. This leads to slow recovery, wasted time, and bad user experience. And these are actually things that we've experienced and analyzed in real traffic. And it's one reason why we have a different approach for Loon. Next chart. Okay, so now we start to talk a little bit about what we do instead. So we leverage the fact that even though there's a lot of motion in the distribution layer in the middle of the network, it's actually fairly predictable. It follows laws of physics usually. So this is true for satellites, for controlled flight, ships on the ocean, and many other possible types of network elements. We use a big set of predictions about the whole network, and then can use centralized decision-making to do global optimization for the entire network. This is in direct contrast to like brittle distributed algorithms that only have a partial and usually stale view of the network, and they don't have any model of motion or how other things are moving in the network. So we take this information and we can integrate radio resource management and capabilities for dynamic spectrum access along with antenna and beam pointing and network routing. So it's a unified system that spans layers. We signal planned changes coherently to the routing system throughout the entire network. So everything happens in concert, sort of horizontally and vertically across all protocol layers and all sets of nodes. We call this temporospatial software-defined networking, or TS-SDN for short, since temporospatial software-defined networking is kind of a mouthful. We implemented this TS-SDN technology in our Loon SDN controller for our HAPS network, and we also offer it for other operators. Next chart. So this is what it looks like. Users will see a network operator screen like this, with a view of how physical assets within the network are arranged, how they're oriented, and how they're expected to be moving. They can see what RF resources are in use and radio configuration details. They can also see how flows are routed over multiple hops through the network, and how those routes that have been selected meet the demands of user traffic flows. Under the hood, there's a physics engine with models of all the network elements. There are algorithms for decision making that run based on all the collected information. And this needs to all be done securely, of course, and we've designed it to run for networks that require high availability and planet scale. Next chart. Okay. So our TS-SDN approach takes aspects of normal SDN technology and extends it. In case you don't know, normal software-defined networking has actually become pretty mainstream in terrestrial networking over the past several years. SDN itself is an approach that we like, and we leverage some good aspects of it. SDN brings the needed centralization and moves away from the decentralized decision making. And it also takes advantage of the flexibility and programmability that exist in the network devices. Some challenges we have, though, are that traditional SDN still has this idealized notion of the network devices themselves and connectivity being fairly stable between them. It works well for wired networks, Ethernet and optical types of networks, but isn't as strongly suited for the types of networks that we're working with. So we build upon the ideas from traditional SDN technology, and in TS-SDN, we've created our own airflow protocol that works between the control layer and the infrastructure layer. This improves on the timing coordination of changes in the network, and it expands the scope of the controller to allow it to work with antennas and radio systems in the infrastructure layer. We also support better advanced planning, distributing control instructions in advance so that since disruptions can be predicted and routed around proactively, we have the information pre-placed in the network so that things don't experience as bad of a hiccup. And this is instead of the way that traditional networking works, where everything in the network has to sort of individually work hard in order to continuously be probing and trying to detect and react to all the possibilities. We have the controller figure things out in advance. A big aspect of this is that all the information from the controller can also be provided up to business applications, and this can be done predictively and proactively. So it helps the applications to improve their own experience because they know more about what's going to happen in the network. Next chart. Okay, so to do this well, our Loon SDN controller needs decent models of the lower layers of the network, and much more detailed than what typical SDN controllers would do. So it knows about things like antenna patterns, slewing rate constraints, obstructions that exist, and other properties of the physical network, as well as how things are moving and their planned motions. It also models the flexibility of each piece of radio equipment, important for dynamic spectrum access and needed in order to plan compatible center frequencies and bandwidths for the channels. Then propagation modeling is used with all this information in order to figure out power levels and make communication system performance predictions through computing link budgets. This can use weather data to take into account not only the free space path loss, but also atmospheric absorption and losses due to clouds, rain, and fog. In terms of dynamic spectrum access, the RF link modeling is mostly relevant, but the system also has the ability to model and control free space optical links for either optical or RF link models, the weather data that's coming into the system to be used. It can include both measurements from sensors in the field and also weather forecasts or predictions from multiple sources. And finally, this approach is cloud computing, since it involves processing a lot of data, analyzing multiple possibilities, and doing a good deal of math. It's been designed to scale up in order to handle large networks, such as LEO mega constellations, and to model huge numbers of things. So it can actually work for multiple systems at once, and even prevent interference between networks in a multi-tenant type of usage. So this is a context illustration for how the Loon SDN controller in the middle operates as a software as a service in the cloud, both for ourselves and for other operators. At the top, there are network operators and infrastructure providers as the customers of the Loon SDN. They use a northbound interface labeled NBI that we provide, and they use that to talk to the SDN controller. They express the needs of their application flows that are going to be on the network, and they receive information back about the network itself and the plans for the network. This is also where they would express policies and constraints related to spectrum management. At the bottom are elements of the physical network, and also virtual network functions and other configurable things that maybe aren't physical but have to be orchestrated as part of the network. Everything that's a network element has an agent that connects to the controller through a CDPI. That's the control to data plane interface. And that's the airflow protocol that we had on a prior chart. So these agents accept control directives and also report their state, which we call network telemetry, back to the controller. Within the controller, running in Google Cloud infrastructure, we're ingesting all kinds of information on the network elements, as well as the weather data measurements and predictions, and feeding this through wireless propagation models to determine all the feasible RF link configurations for the network and how each of them might perform. And that is a large universe of possibilities, especially for networks where there are thousands of infrastructure nodes. And they can articulate the antennas and beams in many different directions. So this is done in a massively parallel fashion. The set of options are fed along with the service request information that the applications have provided to an optimization engine that in a unified way plans all aspects of the future network. That includes the topology, what nodes are talking to what other nodes, the routing, and the radio resource management for the network. The plans or decisions for the network that are generated are then installed through the CDPI across all the relevant elements of the network as they individually need to be updated or changed. They each receive their own directions, and even though the controller has built a plan for the entire network, they only receive the instructions that they need to individually follow. Next chart. Okay, so for dynamic spectrum access, the interference avoidance capabilities of this approach and the system are really important. First of all, the plans that the network creates include all the relevant information to be analyzed against radio regulations and other policy constraints. So the controller can ensure that it never instructs the network elements to do anything that would violate these general rules. Basically, link possibilities that would violate the rules are filtered and not even fed into the optimization engine. So this can apply to single links, like in terms of pointing constraints and PFD limits, as well as the network as a whole, such as in terms of aggregate PFD. Also, the controller has access to information about other specific systems outside the network being managed through external databases that it imports. So this includes things like locations of radio astronomy apertures, other E-band point-to-point links that are registered in databases, and satellite positions and motion vectors, just as some examples. It can use all this information to assist in preventing interference to specific other systems by having a wider view of the dynamic context that the network operates within. By combining the routing decisions with the spectrum and radio resource management, the controller can actually predictively avoid doing things that would cause interference in the future, and it can use other options to route around these types of events if it thinks they would occur. Well, the goal is to predictively do all this perfectly and avoid causing interference. If it should happen to occur anyways through some unknown causes, the results will show up to the controller in network telemetry that it's reported up through the CDPI I was talking about. And that will show up as unexpected measurements or performance metrics. In this case, the controller triggers a replan to take this new information into account. And so this design is actually robust to having an imperfect view of what other systems not under the scope of the controller are doing. It can always sense problems as deviations from its predictions and then react to them. And I think this is my last chart on the technical aspects of how the SDN technology works. And I think I am going to turn it back to Martha to moderate questions.
Thank you very much, Wesley. It's very exciting to see all the engineering behind the system. So thank you for this presentation. We had a few questions. The first one, and I think you covered at the end, but please, maybe you can give more details. Could you please expound more on high dynamics?
So on the balloons?
I guess so, yes. It doesn't give more details. That's the question. Okay,
so our balloons move both vertically and they're blown by the winds. So their motion, like I say, follows laws of physics, so it's predictable, and it's modeled in the system, so we know where a balloon is going to be.
Okay, thank you. We had another question that was answered in the chat, but just for those that may miss the question and the answer. So the question was, is any work being done with any organizations such as IEEE to develop a protocol to help with this issue? And the answer that was provided in the chat is yes. IEEE 1900.5 has been working on this span for over a decade. Do you want to add something else to that answer?
Yeah, that's true. And so we're actually participating in 1900.5. And there are two things of particular interest there. There's the 1900.5.1 protocol, or a policy language for expressing policy. And we're looking at using that in the northbound interface of the system. So applications can actually use that standard to express their spectrum policies to the controller. And then a second aspect is 1900.5.2, which supports spectrum consumption modeling. And so we're looking at supporting that as well, and we're participating in those IEEE working groups.
Okay, thank you. We had another question. What are the parameters for balloon-to-balloon communication, such as maximum distance, RF frequencies, etc.?
So those are E-band point-to-point links. And Jameson, I don't know if you could share the map again, but that would provide a good reference on some of the distances that we typically achieve with those point-to-point links.
Sure. There we go.
Probably, oh, go ahead.
Yeah, so I don't know if this helps answer the question and put it into perspective, but the individual balloons are labeled, and each of the balloons has a dish that it points at either, or multiple dishes that point at other balloons or ground stations. And so you can sort of get from the geography here a sense of the lengths of the links that we're typically making.
Okay, okay. Thank you. We have other question that is asking, do devices require new radios? And how many devices can one balloon accommodate?
So I think that's, there are some details that we're probably not able to share, but in general, I think what we showed is that the balloons implement an eNode B for providing LTE services, and they also have multiple support for multiple E-band crosslinks with other balloons or ground stations.
Okay, here we have we have many questions, that's great. Is the cloud compute done mostly for positioning, or does it play major roles in networking issues as well?
Yeah, that's a good question. So it is used for everything. As you can imagine, computationally, global optimization algorithms often take a lot of horsepower. And so for large size networks where we have thousands of nodes, and each of those nodes may have dozens of radio systems and antenna beams that can be pointed, and we're analyzing all of the possible places those beams could be pointed, and how the RF propagates, and what other systems it hits, and what the power levels that are received by those other systems are. There's a lot of computation going on, and when you run an optimization algorithm that is analyzing all the different possibilities and walking through them, it uses a lot of memory, a lot of compute, and that's why we leverage cloud.
Great, thank you. I think I still have some questions that would be very useful to clarify to everyone as a final tech. What specific bands are used? Can you please reinforce that concept to explain?
So I think Jameson actually addresses that really well in his upcoming charts. So I think I'll defer that to him.
Sure. Yeah, and I'll talk more about that. So we use the E-band for backhaul, and as I mentioned before, we use LTE for the access side. I'm going to focus on E-band in my talk.
Yeah.
So that's 71 to 76 and 81 to 86 gigahertz.
There is another from Stephen Talbot, so I will defer that after your presentation because it is also related to that part of the system. Another question. Well, these are there are some questions that will be more related to policy, so we will take them after. Could you please repeat about the standard 1900.5.2? What is it studying?
It's spectrum consumption modeling, and we use it for so it can represent things like antenna gain patterns and underlay masks that need to be understood by the controller.
Thank you. How does the system deal with conflicting wind forecast models?
So that's a good question. Yeah, so when you're dealing with measurements versus predictions, and especially ingesting multiple sets of predictions that can conflict, that happens, and there are algorithms for dealing with that we use. I don't have much information on that today to share.
Okay. You mentioned that SDN controller is powered with artificial intelligence. In which kind of task is it this power?
So it's fairly widely applicable, and we've been using different approaches actually in multiple internal pieces of the controller. One place where it's very obviously applicable is in the production of the future optimum network configurations, since you can learn from the past and attempt to predict future states based on that. And so, yeah, we've been using machine learning technology in the definition of the algorithms that are used there, and you can also use it to analyze the performance of the links over time, and whether there are unexpected things that that might be about to happen there.
Thank you. I will just take a couple of questions and we can move to the policy part. What is the maximum LTE payload weight that the platform can support?
That I don't know off the top of my head.
Okay, maybe we can have some feedback at the end.
Yeah.
And this one, how do you manage the pitch roll NAT-YO in LoonNet?
Okay, so the SDN controller knows not only the positions of things, but also their attitudes, orientations in space. And so the assumption is that vehicles can have some control over that, so that the controller, as it's modeling the attitude of a platform, is doing so accurately.
Okay, so there are still some unanswered questions. Thank you to all the participants. This is great. But now we will move to like the next part of the agenda, creating and enabling regulatory environment for aerospace networks through dynamic spectrum management. So Jameson, please, can you present that? The floor is yours.
Sure thing. Can everyone see the screen? See the slide
deck? Yes, we can see it.
Perfect.
Yeah.
Okay, great. Thank you very much, Martha. Thank you, Wes. And thank you to everyone for all of your amazing questions. I'm sure we could go on all day just on the technical side. I'm here to talk about policy, and specifically to talk about the suitability of millimeter wave bands like E-band for dynamic spectrum access. Let's dig into it. So regulators have long recognized that the unique nature of millimeter wave bands such as E-band. The US Federal Communications Commission recognized in 2003 that due to the high gain directional nature of pencil beam point-to-point systems within E-band, links, quote, may be engineered to operate in close proximity to other systems so that many operations can coexist in the same vicinity without causing interference to one another, unquote, particularly in less densely populated rural and suburban areas where there's quote, an even lower chance of interference. The unique nature of E-band also enables coexistence of ground-based and aerospace systems, particularly for aerospace systems such as Loon that typically deploy ground infrastructure outside of urban areas. A recent coexistence study from ComSearch, one of the two E-band database managers in the US, found that except in cases of direct antenna alignment in azimuth and elevation, interference from aerospace links above a 5-degree elevation angle would be rare. Reflecting on that study, Qualcomm found that even at elevation angles as low as 1.5 degrees, the highly directive nature of air-to-ground E-band links would not cause interference to ground-based point-to-point links. Moreover, systems such as Loon, as you just heard from Wes, can take things one step further through TS-SDN, programmatically ensuring that inline events never happen. Now, for these reasons, there's been significant interest from aerospace networks in using E-band for backhaul, including stratospheric internet platforms such as Loon, in-flight broadband backhaul, and also NGSO satellite constellations. Loon welcomes this emerging hybrid connectivity ecosystem and believes that all systems can coexist within the band. In fact, colloquially on our policy team, we think of the E-band as the everybody band. Now, E-band not only has technical advantages, it also has regulatory advantages that make it attractive for aerospace networks. First, as you can see in the table of frequency allocations on the right, There are co-primary allocations for a number of different services, including fixed service, mobile service, the fixed satellite service, the mobile satellite service, and more. In addition, E-band has a particularly flexible recommended band plan to enable providers to use multiple gigahertz of bandwidth in both the uplink and the downlink while coexisting with all other services. And these features make the band ideal for aerospace backhaul, which requires significant capacity to extend networks into unserved and underserved areas. The unique propagation characteristics and flexible ITU regulations for E-band have led to significant innovation in licensing at the national level. For example, as you can see on the chart here on the left, a number of national regulators have adopted light licensing frameworks for E-band. These frameworks enable a provider to seek a non-exclusive nationwide license to use the band anywhere in the country, and then to register individual links on a self-coordinated basis with other users of the band. Since the early 2000s, the United States has relied on third-party database managers and an automated process to enable rapid deployment of fixed services in E-band. And you can see on the right-hand side exactly how the US does it. I'm not sure if this is big enough for everyone's screen. I tried to make it large, but this flowchart comes from DSA's Automated Frequency Coordination White Paper, which if you haven't read, absolutely recommend reading. You can see the flowchart, the process for link registration in the US. And unless the link is flagged for coordination with NTIA, which manages the federal links, it's generally an automated process that allows users, the licensees, to self-coordinate and then register their own links in an automated database system that's run by one of two database managers. But this raises an important question. This framework was designed for point-to-point links on the ground. Can this flexible light licensing framework accommodate other use cases? For example, to enable the deployment of aerospace networks? Well, the answer is yes, and the FCC is currently exploring how to do just that. I apologize for all the text, but I'll make it as lively as possible. So specifically, the FCC this year issued a notice of proposed rulemaking that proposes to authorize quote-unquote antennas in motion or endpoints in motion in E-band. Antennas in motion are point-to-point links between a ground station and a moving station someplace in the air, and also links between those moving objects. The petition for this change was made by a company called Aeronet, which seeks to create meshes of aircraft stations for in-flight broadband and also for rural connectivity on platform stations existing up into the lower stratosphere. Now, in the NPRM, rather than construct an entirely new licensing framework for these airborne platforms, the FCC proposes something novel. It proposes to incorporate antennas in motion into its existing link registration framework through something called 3D spectrum management. But how would 3D spectrum management work? Well, nothing has been confirmed, but ComSearch, one of the E-band database managers, recommends incorporating airborne stations by registering non-exclusive three-dimensional coordination zones around ground stations to facilitate coordination. Now, creating these 3D areas is actually relatively easy. All you need to do is add a few parameters to the link registration database for the links. For example, by adding an elevation angle range and an azimuth range, you can create what you see on the right-hand side of the slide here. It's essentially a non-exclusive cone around the ground station that can ensure coordination and coexistence between these airborne links and fixed service links on the ground. And these small changes to the database would enable all sorts of innovation, not only links to aircrafts operating, or aircraft such as commercial airplanes, but also moving links on stratospheric platforms, so long as the object can be represented in one of these non-exclusive areas and operate within one of the non-exclusive areas, and that there is adequate physical separation between ground stations, you can ensure that there won't be interference between incumbent links and future services, including aerospace networks that are deployed in the band. Now, in response to the NPRM, there has been strong industry support for sharing between ground and airborne links. For example, the Fixed Wireless Communications Coalition and the Wireless Internet Service Providers Association, which both deal with ground-based point-to-point networks, support expanding E-band to incorporate antennas in motion. The Satellite Industry Association, Scientel, and Qualcomm, and ComSearch, which runs the database, have all argued for a comprehensive E-band database. They say the database should incorporate all services to enable efficient coordination and coexistence of all the services in the band. And as a reminder, all of these services are co-primary within the band, which creates incentives for coexistence rather than prioritization. Importantly, a number of parties also supported setting a pathway toward dynamic spectrum sharing in the band. In Loon's view, databases that include real-time or predicted information about where moving links actually are or are going to be could enable even more efficient coexistence between all of these systems, including coordination between multiple aerospace networks and air-to-air links between those. In fact, as Wes mentioned earlier in the presentation, that's exactly what our temporospatial SDN does today for our own network and for our partners' networks. So some of you might be asking, well, what's the first step? What can a regulator do right now in order to set a path toward coexistence of networks on the ground, at sea, in the sky, and in space within E-band or other millimeter wave bands? Now, the answer starts with data. So if as a regulator you don't have an updated database already, the first step is to conduct a spectrum audit to determine how the band is being used. Ask questions like, where are the links located? What are their parameters? What are the elevation angles or the azimuth ranges? You can see some examples of things to figure out in the box on the right. Next, once you've conducted the audit, you can use that to populate or update a comprehensive database of all the spectrum usage in the band. We recommend making that database available online or through a third-party database manager in the US, for example, like ComSearch. An online database can facilitate automated self-coordination to promote efficient network planning and rapid deployment. After creating the database, the next step is to update the link registration process to accommodate all services in the band. For example, a web-based link registration process can serve as an input into the database. Think of it like an end-to-end solution. That would streamline the process for link registration and would enable more efficient spectrum audits in the future. With an updated database, you can just check the database against what's going on the ground rather than starting from scratch each time. Moreover, regulators can adopt something like 3D spectrum management by incorporating some of the parameters that I mentioned before, things like antenna height, elevation angle, and azimuth range in the application process. And this is just a start. Over time, database managers can incorporate real-time data on the movement of aerospace links to enable even more efficient coexistence of all services within the band. So to conclude, I'd like to highlight 3 reasons why I think that TS-SDN is an exciting development for dynamic spectrum management and for regulators. First, the software enables efficient coexistence of both fixed, mobile, and satellite point-to-point networks, including 5G backhaul, NGSO satellites, aeronautical uses, and stratospheric internet platforms such as HAPS. This is really good news for the millimeter wave bands, which multiple operators are exploring for backhaul and feeder links. Second, TS-SDN and systems like it build upon important work that regulators have been doing to make spectrum licensing more flexible and transparent. Specifically, the availability of aerospace networks, or the ability, rather, of aerospace networks to effectively avoid interference depends upon the accuracy of the underlying data, including information about incumbent licensees and where their links are. As we explained today, a number of countries have already developed self-coordinated light licensing regimes for E-band that enable operators to efficiently plan their networks, register individual links, and deploy infrastructure. As regulators continue to adopt light licensing regimes for millimeter wave bands, it will enable more efficient use of spectrum and the deployment of aerospace networks to close the digital divide. Third, and finally, software like TS-SDN shines a light on a future path for dynamic licensing of backhaul networks. TS-SDN demonstrates that efficient orchestration of heterogeneous networks is possible with the right data and the right software. And this is really exciting for regulators looking to maximize the utility of millimeter wave spectrum to drive 5G and to drive rural connectivity. By working together, industry and regulators have an incredible opportunity to make this future a reality. So I'd like to thank you all for your time. I'd like to thank the DSA, and then for the balance of our time, we're happy to take any questions you may have. Thank you.
Thank you very much, Jameson, for this presentation. So we definitely have a lot of questions, and let me move to them. Okay, so 1 second, please, because I need to make sure I cover them all. So we had 1 second. Sorry, here. Is the SDN completely customizable to fulfill the regulations needs in each country?
So the answer is over time it will be, but it really depends on the deployments, and it depends on the availability of the data. In many countries, E-band has not been deployed for fixed links. And in other places, it requires working together collaboratively with the regulator to understand where the links are in order to make it work.
Yeah.
Wesley, yeah.
I would also add, this is another reason why the northbound interface I talked about, we allow the operators to express the policies that their networks need to be held to. And so it's variable. There's not hard-coded logic for policies in the controller. So it's intended to be dynamic, flexible, and variable across the globe.
Yeah, and I think I would like to highlight the importance of preparing and organizing the data. I think that is relevant and crucial to be able to have these kind of solutions implemented in the long term. There is a question also. So hello, very interesting. This person has been watching Loons via the Fly Radar 24 app. As a regulator, he knows that the band range is E-band. So he's assuming that this is the terrestrial ITU allocations. Can you be more specific about that?
I'm sorry, could you repeat the question or clarify the question?
The question is exactly like, is the band, so the Loon is using the E-band, 60 to 90 gig. And is it the terrestrial ITU allocations? Can you be more specific on that?
Sure. So yeah, so we do use E-band for the links, so 71 to 76 gigahertz and 81 to 86 gigahertz. Typically, it is in line with the deployments that we've done already, or the work that we've done already is in line with the fixed service allocation in whatever country where we're operating. And then we operate pursuant to a duly issued license from that regulator in order to deploy.
Is the E-band just for Loon to Loon communications or Loon to ground as well?
Both.
Okay. Let me see, because there are more questions here. What are the LTE bands that have been used for Loon to user connection?
Yeah, LTE bands 20 and 28 is my understanding.
Do you want to say something else, Wes, or that's fine? Okay. Let me see. Sorry, so those were of the questions that we had before. So now let me see. Sorry, it's hard to manage here with so many questions. I apologize, it takes me a while. Some people say that thank you for these answers. No, I think I have covered them all. Just making sure it is the case. Yeah, I was under the impression that there were only a handful of Loons in operation. Was the chart over Peru during the earthquake recovery, or is that current after or is that a current chart?
It's not a current chart. Yeah, and it's an older chart. I don't recall whether that was during the disaster recovery or not, although I'm happy to find out if that's important information for you.
One of the other questions, they mentioned that they look at Flight Radar 24. That's a good place to find how many balloons are active. They're all tracked there, and there's not very much else in the stratosphere, so you can find the Loon platforms pretty easily.
Okay, so those are the questions I have so far. If any of the participants have any additional questions, please feel free to write them here. In the meantime, maybe Jameson, can you describe us a little bit more about the partnerships that Loon has been having in the last months and that has been announcing?
Sure, absolutely. And I encourage everyone to check out Loon's blog. It's posted on Medium. You can read all the details about the recent announcements. We've had an announcement with Telecom Kenya, which is really exciting. And recently did some of our in our first testing, we were able to connect a village called Radap that had never been connected before with terrestrial infrastructure, terrestrial LTE infrastructure, and do a video call from the head of the telecom regulator to the president of Kenya from an area that hadn't been connected with LTE before. It's really, really exciting. So we're very excited about the Kenya partnership with Telecom Kenya. Another recent partnership, which is really interesting, it's a global partnership with AT&T to provide disaster recovery. So it's in essence a roaming arrangement. So anyone who has a roaming agreement with AT&T would be able to leverage our balloon network in order to provide disaster recovery solutions. So this is really exciting. You can read more about that. We have a number of other countries in the pipeline, as I'm sure you can see if you read through on the blog, but we're very, very excited to begin deploying these services commercially, to work with great partners all around the world, and to achieve our mission, which is to connect people everywhere.
Yeah, that's very exciting. And yeah, I know that there is a lot of interest from different regulators. There are a couple of additional questions. One is, how do you manage the TLEs considering rock satellites?
Could you repeat that question, please?
TLEs, so those are the 3-line elements or 2-line elements for the satellite positions that we typically import those from external databases for satellites that are not operated by someone who's already using the northbound interface and giving us their satellite plans and current state vectors. So we rely fully on other parties that are tracking something like a rogue satellite. So in the US, the NORAD does that, and the database that they provide access to, we import data from.
Okay, thank you. What is left for Loon to figure out in the electrical engineering realm? Future perspective.
That's a good question, and I don't know if we have an answer to provide right now, but we appreciate the question. Like you know what? What's left to figure out is how many people we can serve, and how best to achieve that, and how we can work with our partners and with regulators to make that happen.
Yeah, I think that's an important next step. Here is a very specific one, but maybe you can give us some lights. Regarding the Loon operating right now in Africa, are they allowed to overfly Tanzania? I don't know if you have those details here.
That's a good question. You know, I'm on the telecom regulatory team. I don't know if I have an answer to that right now, but I could check with the overflights team.
Mm-hmm. had Loon any advance on the operation in Mozambique? It seems that someone is particularly interested.
What was the question? I'm sorry.
Had Loon any advance on the operation in Mozambique?
Had Loon, I'm sorry, I don't know if I understand the question. If you check out on our blog, you can see about the announcement that we made regarding Mozambique.
Okay. This is interesting. Dynamic EBAN registration scenario. How would you motivate participants to operate in good faith to only register for the bands and vectors that they are actually using or planning to use or plan to use?
Yeah, it's a fantastic question, and it's one that the FCC is trying to better. It's one the FCC has been grappling with and trying to deal with, including in this proceeding. So the good faith effort, I think a lot of it has to do with the relationship with the regulator. So whether that's conducting spectrum audits to make sure that the links are actually being used, having a sunset period on registered links to make sure that the links have been constructed. And then to the extent that you're using a temporospatial system, like the one that we have, then there would be data about whether the bands are actually being used or whether the links are actually being used. So I think all of those things together promote a good faith operation, whether it's a regulatory backstop, technical data, or periodic spectrum audits.
Yeah, this is just a confirmation. Are most of the positions of the Loon's position software based?
Could you say that again, Martha? Sorry.
Are most of the Loon's positions software based? So is that mainly, I mean, is it controlled all the time by software to know exactly their positions?
Oh, I think that would be. I think that's a Wes question. I think that, I mean, we have telemetry on the balloons, so we know where the balloons are. We know where the balloons are.
Yeah. So
okay.
Obviously there is a lot of software in the system that we have for the temporospatial SDN, since it's basically purely a software system. There are also aspects of Loon that are very hardware oriented, like people build the balloons themselves, and there's mechanical, electrical, and other types of engineering and design analysis that happens there, which is also not done by software engineers. So if right now most of the job postings I think they're saying are for software engineers, that may be the case, but it doesn't mean that Loon is only software.
Here we have another one. Which frequency bands other than the E band do you think would be suitable for HAPS feeder links?
So I'm not an engineer, but we've talked to engineers on our team about this. We think that when it comes to aerospace networks, E-band has particular advantages. Apart from E-band, there are other millimeter wave bands that have been explored and authorized for HAPS feeder links. One would be the 39 gigahertz band. It's in a similar position in that there are co-primary users on the satellite side, on the mobile side, and then also for fixed links as well. So it's similar to E-band, but it doesn't have all of the advantages that I mentioned earlier that the E-band does. So I think 39 gigahertz is another example.
Okay, great. People were asking also about the blog and where they could find more information. So I think the links have been shared with the audience. And well, I think we are just at the end of the session. I would like to thank you and thank all the participants. We had at some point we had 80 attendees, so that is a great attendance. And I'm very glad for the questions. It really shows the interest of the audience on these subjects. Thank you, Jameson. Thank you, Wesley. Do you want to give a final message, each of you, just before we conclude the session?
Wow, an opportunity for a final message. Yeah. Well, I think my final message has two parts. First is gratitude. Thank you very much, Martha. Thank you to the DSA. Thank you to everyone who joined today. Thank you for fantastic questions. We really appreciate this opportunity to talk about our system, to talk about how we operate, and to talk about how we're trying to achieve our mission in partnership with regulators and with our partner operators all around the world. So thank you very much. But I think that the message I'd like to convey is that it takes everyone working together in order to build this third layer of connectivity, to build this hybrid ecosystem that brings together ground-based, aerospace, satellite networks harmoniously, particularly in bands such as E-band. So we look forward to working together with you and expanding Loon's network all around the world in order to achieve our mission and many of the policy goals that regulators have. So thank you very much.
I would just say there's more to the TS SDN technology than we could have jammed into this session. So people should check out the loon.com website. There are links there under the technology and the solutions headings about our SDN and our network orchestration capabilities.
Great. And final message also from my side is like, thank you for showing the engineering behind and how I think this will be really, really important in the future, how we could have like more intelligent systems managing data and making sure that we can make a very, very efficient use of the spectrum. So I really appreciated this 3D spectrum management vision. So thank you for sharing that with us today. And thank you to all the attendees. I hope you enjoyed the session, and we will post this video so you can also share it with your colleagues. And so I hope you will register for the DSA Summit, because that will be a great opportunity to have more details about spectrum sharing in different frequency bands and using different technologies. So thank you and have a nice day. Bye-bye.
Thank you.